All right, so I'm going to freestyle with you for a little bit, AP Chem style, so sorry, not rapping. Um, this, what we're going to end up leading into is the chapter for salts, and I just kind of want to do a basic review of what salts are. So salts. For us, right now, for the sake of this class, they're anything that's ionic, okay? A cation and an anion shoved together to make a salt. And you should know that salts are also a product of acid-base neutralization problems. For example, HCl, strong acid, NaOH, strong base, produce sodium chloride. That's your salt, and water. Okay? Now, strong acid, strong base will always produce for you a neutral salt. And by neutral salt, I mean if you put this salt in distilled water, the pH of this salt solution will be 7. Okay? Now, this is not true when you have a neutralization between a weak acid, strong base, or weak base, strong acid. The salts produced are not actually neutral salts. You can have acidic salts and you can have basic salts. If you remember back to the weak acid, strong base titration, the salt produced was a base. Okay, and it was went into hydrolysis with water, and that's why you ended up with a basic pH at the equivalence point where all you had was salt and water. That salt was basic. So I'm going to go over a few cheating ways, no math, just cheating ways of how to recognize whether a salt is acidic or basic. So I'm going to give you a salt. I'm going to throw you a random one. Pulled it out of the top of my head. Okay, here's what you do. You cheat. Okay, you're going to rip the salt apart. You're going to work backwards. Sodium nitrate. +1, -1, right? Cation, anion. Always throw the cation with hydroxide to make it a base, and always throw the anion with a hydrogen to make it an acid. So the sodium came from sodium hydroxide, and the acid came from HNO3. I threw the hydrogen on the nitrate and the hydroxide on the sodium. Hydroxide's always negative, so you want to throw it with the cationic part of the salt. Hydrogen's always positive, so you want to throw it with the anionic part of the salt. Sodium hydroxide plus nitric acid make sodium nitrate, salt, and water. Excuse my dog. Todd. His name's Todd. He doesn't like salts. He's salty about salts. Okay? All right. Here's the deal. Strong base, strong acid will always produce a salt with a neutral pH of 7. Okay? Now I'm going to take a salt, sodium fluoride, for example. And I want you to predict whether it is a basic salt, acidic salt, or a neutral salt. So again, I need you to work backwards. Sodium hydroxide is going to be the base that makes my salt. And the ionic part I'm throwing with a hydrogen. So hydrofluoric acid. So this salt is a product of a weak acid, strong base. This is a basic salt. The strong overpowers the weak. So this salt would have a pH greater than 7. It is a basic salt. Okay? Let's see. Let's try this guy. Ammonium chloride. +1, -1. So again, rip it back apart. Ammonium, the plus goes with hydroxide, and the hydrogen goes with the chloride. Ammonium hydroxide, hydrochloric acid make ammonium chloride and water. Weak base, strong acid. This is an acidic salt. It would have a pH lower than 7. It would not be neutral because it is the product of a weak, strong reaction. Okay? Let me try one more. Let me think if I can pull one up off the top of my head. Magnesium nitrate. So magnesium, remember magnesium's +2, so you'd have to write the base like that, magnesium hydroxide. Nitrate is -1, so this would be HNO3, right? Weak base, strong acid. That was what this salt would be made from. This would be an acidic salt. Are you picking up what I'm laying down? Okay, acidic salt. Okay, so salt problems are really easy if the salt is formed from a strong base, strong acid. Their pH is 7. However, it is not as easy to calculate the pH if they are not, the cation and anion don't originate from strong species. So the point of this page is to show you how to do it when it is not a strong base, strong acid producing the salt. When one of them is weak and one of them is strong, it is done a little bit differently. In fact, it is done almost identically to the equivalence point of a weak-strong titration, because that was calculating the pH of a salt at the equivalence point. So here we go. Are you ready? No. Okay. Here we go. All right, calculate the pH. Ooh, that's kind of funky. Of a 0.1 molar, and this, I'm going to rewrite this, KC2H3O2. All right, so the first thing you always do in this is identify the major species. Well, the major species is C2H3O2, which is a metal and a polyatomic, also known as ionic, also known as a salt, meaning this is a salt problem, okay? I don't see a weak acid anywhere right now. I don't see a weak base anywhere right now. I see an ionic compound, okay? So what do you do after you identify the major species? We always write out the reaction, right? Well, in this class, we always assume salts for the sake of right now. Oops, C2. 100% ionize in solution, right? So the salt would break apart into its respective ions, the potassium ion and the acetate ion, okay? One-way arrow, this is ionic. It's not equilibrium. This is not weak. This is ionic, okay? Now, this is the very, 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 very important part, and this is where most mistakes are made on this problem. I need you to think backwards. I don't need you. You could do this kind of on the side. The K comes from potassium hydroxide. The acetate must come from acetic acid then. Okay? Strong base, weak acid. You should know at this point off the bat that you should get a basic pH for this salt. Strong base, weak acid. Okay? Now, we are not focusing on these guys. Okay? This is where the mistake is always made on these. I am not focusing on them in terms of like a reaction. All I want to know is you need to identify the weak part of the salt. The weak part of the salt is this guy. It comes from the weak acid. Okay, it's the conjugate of the weak acid. And in fact, I shouldn't have said it that way. If this is a strong base, this is a really, really weak, okay? Okay, rechecked all that. The weak acid gives us this conjugate. I'm focusing on the weak part right here, not the strong base part, okay? So what you do next is you take that weak part of the salt. This is of the salt. This is where the kids make the mistake. They start writing acetic acid down here. Acetic acid is not part of the salt. This was just us backtracking in our brains of how this salt would have been produced, okay? And you let it undergo hydrolysis, okay? Hydrolysis. So this part of the salt, the weak part, undergoes hydrolysis. Okay, now weak, so equilibrium. Now, this is also important. Remember, potassium hydroxide and acetic acid make potassium acetate. So if this is a weak acid, this part of the salt, though, is a base. It would be the conjugate base. Okay, we need to know that because we need to know what our products are going to be. What do bases do? They accept hydrogen ions. So you get this, and the water loses the hydrogen ion. It acts like the acid in that instance. Okay, ICE. Now, remember, for salts, if it's 0.1 molar potassium acetate, it's 0.1, I'll do this right here. It's 0.1 molar this guy and 0.1 molar this guy because salts are assumed to 100% ionize right now. So this guy is 0.1 molar. This is a liquid, we don't care. 0, 0. Okay? And then you go, oh, but people calling me right now? All right, then you go, what about the acetic acid? Well, the acetic acid is not in here. What we have in here is a salt, just a salt. Again, this stuff up here was me backtracking in my brain trying to figure out which two things formed the salt that we have. Okay, so here we go. This is a very, very basic, I love my basic jokes, ice chart. We're going to let x equal something. X minus x, right? All right, set up your equilibrium expression, right, for this thing. So you have x squared over 0.100 minus x. We assume x is small, so it goes away. Equals products over reactants equals K. Now be careful, we had this issue during the titration problem also. This is acting like a base, so we have to have Kb. I didn't give you Kb, I gave you Ka. Up here I'll show you, remember Ka times Kb is 1 times 10 to the negative 14th. Plug in Ka, divide both sides by the Ka. Kb is 5.68 times 10 to the negative 10. Rearrange cell for x. X equals looks like I have 7.5 times 10 to the negative 6th molar. Well, X is my hydroxide ion concentration. So I'll go over here. POH equals opposite the log of 7.5 times 10 to the negative 6. So POH is 5.122 is what I'm looking at. So pH is 14 minus that number, so 8.888. Is that right? I guess that's right. Notice that is a basic salt. The pH of this salt is basic. Why is it basic? Because it's made up of a strong base and a weak acid. So the strong overpowers the weak. So again, be very careful. You ionize the salt completely and take the weak part of the salt. Okay, the weak part of the salt. Not the weak acid or the base that made the salt, just the weak part of the salt. And put it through hydrolysis with water. And that is how you do a salt problem. So I actually have a second example because I want you to get really good at this. So we are going to try one more example together. Ooh. Ooh. Aha, there we go. All right, I'm asking you to calculate the pH, and I gave you a salt. How do I know? Ammonium +1, chloride -1. So first thing you always do, identify the major species. Ammonium chloride, it's ionic, so it's a salt. Okay, write out the reaction. Now there isn't really a reaction. It's not reacting with anything. It's just a salt solution. So in this class we assume most salts 100% ionize. Right now we assume that. Okay, so it breaks apart completely into ammonium and to chloride, strong electrolyte. Okay, so really when it says 0.1 molar ammonium chloride, it really means 0.1 molar this, 0.1 molar this. Okay, so it is your job now, in order to figure out the pH, to work backwards. So you go off to the side. What you're about to do is not going to be any part of your reaction. Ammonium. Where did the ammonium part of the salt come from? Always put the cation with hydroxide. So there's my base. Okay? Cl. Remember the anion you're always going to throw with a hydrogen. Okay? So HCl. There's my acid. Acid, base would give me ammonium chloride and water. All right? So this salt is formed as a product of a strong acid, weak base. So you better end up with an acidic pH because the strong acid is going to overpower the weak base. Now because this is my weak part of my salt, this is who I am going to use to write my equilibrium with. Ammonium with water at equilibrium. Now, be careful. Oops, I forgot the plus right here for ammonium. You have to know how ammonium is acting. Well, if this ammonium hydroxide is the base that was produced, or that was used to produce ammonium chloride, if this is the base, this guy right here is a conjugate acid. So this is going to act like an acid. What do acids do? They lose hydrogen ions. So you end up with NH3. Well, who took the hydrogen? The water, right? So the water now ends up being H3O plus. Okay? Set up your ice chart, ICE. So the ammonium is 0.10 molar. Water's liquid, we don't care. Nothing, nothing. All right? Let X equal something. Doesn't matter who you do. So this is X, this is X, this is minus X. 0.1 minus X, okay? Set up your equilibrium expression, products over reactants. So we have X squared, X and X. This is 0.10. Remember, we're going to get rid of the minus X. Remember, we never ever put liquids in our equilibrium expression. So there we go, okay? Uh-oh, we have a problem. I didn't look up the Ka value. I guess I would have to give that to you. My bad. Ready? Here's the Ka. Here is, okay, in order to do this problem, you'd have to have the Ka. The Ka of ammonium is 5.7 times 10 to the negative 10. Okay, so that's my bad. I should have given you that piece of information. I will make a note of that for next year. 5.7 times 10 to the negative 10 is the Ka of ammonium. Okay? Now, let's say they gave you the Kb of ammonia. You would have had to turn Ka or Kb into Ka using that Ka-Kb equation. So then here's what you do. You multiply both sides by 0.1. Take the square root to get X. X ends up being, I guess I better plug in my calculator. 5.7 times 10 to the negative 10 times 0.1 square root answer. I'm getting 7.54 blah blah blah. There's actually a lot more bigger numbers. Times 10 to the negative 6th molar. Okay. Well, that is H3O plus, aka H plus. So pH equals opposite the log of H. So opposite the log of 7.54 times 10 to the negative 6. And the pH ends up being 5.12. 2 sig figs. This was a 2 sig fig problem off the bat. So there's my 2 sig figs. Look at that. That is an acidic salt. You have a salt that has an acidic pH because it was the product of a weak base, strong acid, acidic pH. Okay, so again, that is how salt problems are solved. Don't be salty about it.